Today's video is about tablets. Not that kind of tablet, this kind of tablet. I'm talking about graphics tablets, designed to let you control desktop and laptop applications with something that looks and feels like a pencil. Graphics tablets don't just sense where you touch, they also sense how hard and sometimes what angle the pen is at, allowing applications to more faithfully simulate the drawing experience with a pen or pencil. You could even use graphics tablets to sketch in 3D using tools like Mesh Mixer and ZBrush. Or you could use a graphics tablet to create a vector sketch right on top of a photo reference using a tool like Illustrator or Inkscape. Vector drawings are especially good when you need a toolpath for a laser cutter or a milling machine. You might already be familiar with another type of device that uses invisible electrical signals for human-computer interaction. This is the capacitive touchscreen found on pretty much all smartphones and most tablet computers. You can use an oscilloscope probe as a simple electric field antenna to see the scanning patterns on a mobile phone touchscreen. As the name would imply, it's based on electrical capacitance. Capacitance is the property that allows two conducting surfaces separated by an insulator to store direct current energy or transmit alternating current signals. Capacitive touchscreens have been especially popular recently because you can easily manufacture them by printing layers of conductive transparent oxides on the back of glass sheets. This is a very simple model of a touchscreen. It has two electrodes made of copper foil. One's being used as a transmitter, one's being used as a receiver. There's a layer of packing tape over the top simulating the glass. This prevents a direct connection between my skin and the electrodes. But when I press down on both electrodes, there's a strong capacitive coupling that actually increases the amplitude of the signal passed from the generator to the oscilloscope. So these capacitors have some pretty nice features. The metal plates can actually just be any old bit of conductive material, even just two wires that happen to be running next to each other. This makes it easy and cheap to produce display touchscreens where one side of the capacitor is your finger and the other side of the capacitor is transparent. Then there's a much more subtle effect where some of the signal that would just naturally go through the air from one electrode to the other gets absorbed by my body as I get close to it. But the effect is very nonlinear with distance, and it can be unreliable to detect hovering above a touchscreen using this very small change. So usually touchscreen controllers are just looking for this very drastic change when your fingers are right on the glass that's coated with the transparent electrodes on the backside. There's a different strategy where the two halves of your sensor become a transformer instead of a capacitor. A transformer uses two coils of copper wire to convert an alternating current into a changing magnetic field and then back to electricity. This is most efficient when the two coils are wrapped onto the same metal core. But you can still use this technique to transmit power and signal through the air over short distances. This is a coil with an inductance of 10 millihenries. Normally you might see a coil like this providing temporary energy storage in a small boost converter. But here we'll be using it to transmit and receive signals made from changing magnetic fields. This is how many RFID cards work, especially older door access control cards. The RFID reader has a coil made from traces on its circuit board, and the card has a coil made from very fine wires embedded in the plastic. RFID cards almost always use specialized chips in order to efficiently use the small amount of power available from the reader's magnetic field. This low-frequency RFID reader uses a 125 kHz sine wave as a carrier wave to power the small chip embedded in each card. The card can send a modulated ID signal back to the reader by changing how much power it uses every few cycles of the carrier wave. But it is possible to make a crude RFID card that returns whatever value we want using a general-purpose 8-bit microcontroller. The coil provides power and a clock signal to the microcontroller, which then selectively loads the coil using its output drivers in order to return a signal back to the reader. So this brief look into RFID cards is showing us a little bit about how a graphics tablet might send power to the pen, and how the pen might be sending information from the sensors back to the tablet. RFID doesn't usually measure position, but other technologies can use coils to measure position quite accurately. A good simple example is the linear variable differential transformer. It uses 3 coils to accurately convert the linear motion of a shaft to the magnitude of an AC signal. So in this video, we'll be looking a little bit closer at two specific graphics tablets. They're both about the same size. This tablet here is made by Wacom, and their name is practically synonymous with tablets to many people. They make very high-quality tablets. Their tablets are also kind of expensive. I first bought a small graphics tablet many years ago when they were first starting to become affordable for non-professional sorts of use. And I ended up using it so much that years later I wanted to upgrade. So I'm shopping around and I see what looks like a pretty great deal on these tablets made by Huion. This Huion tablet was 1/4 the price of a comparable Wacom tablet, so I figured it was at least worth a try. And I did actually use it for a while, but I have both of these primarily because the Huion tablet disappointed me in terms of the driver support. It would often leave keyboard modifiers held down when you were switching windows. Some of these were related to the left-handed mode, which I kind of like to have. For the purposes of this video, it's actually handy that I have both now, because I can demonstrate their different methods of operation. At the very highest level, all tablets work by generating mouse events and moving the mouse cursor around the screen. Moving the pen above the surface causes the mouse cursor to move. Dragging the pen along the surface moves the mouse cursor with the button held down. And usually the buttons on the pen and the eraser map to other mouse buttons. This mouse emulation is a convenient way to navigate your computer while you're using the tablet, but the downside is that mouse APIs really don't have the features that a drawing application like Photoshop or Illustrator would want. At the very least, most drawing applications will want to know about pen pressure so that they can give the option to adjust the stroke's width or opacity depending on how hard you press. As a programmer, the interface you usually get for mouse data is exceedingly simple. Usually just motion and 2 buttons, maybe 3. In a modern computer system, so many different layers of software are involved in making the mouse work. From drivers for the mouse itself and whatever I/O port it happens to be attached to display driver support for drawing the mouse cursor, Windows Server support for sharing the mouse amongst multiple applications. All of this bureaucracy provides layers of isolation between the applications and the hardware, but it also comes with its own rigid structure. Linux users might be familiar with the long-standing tradition of emulating the mouse wheel as 2 otherwise unused buttons. Horizontal scrolling is still new enough to be a cross-platform nightmare unto itself. We've had a more flexible way of representing input devices for a while now. APIs for operating systems and GUI toolkits naturally have to change quite slowly. Programmers then replicate the patterns that the operating system set up, and so on. In the late 1990s, the standards behind USB were starting to come together. There was one portion of the USB spec that in particular was trying to address this proliferation of really strange input devices that all use their own custom protocols over the existing PS2 or serial ports. This was the USB Human Interface Devices, or HID spec. HID was a remarkably forward-looking and in some ways naively optimistic specification that tried to cover any conceivable way that you could have a USB device connect between a computer and a human. The vast majority of the HID devices we actually see out in the world are mice and keyboards, but HID was designed to support anything from small display devices to exotic input devices for simulation environments. But despite these tables of optimistic hexadecimal codes for magic carpet simulations and VR devices, no one at the time really could define how those drivers would work, and so no one really wanted hardware that no one would know how to write a driver for. The mouse APIs we use today have in general changed very little since the original Microsoft mouse released in 1983. This was all back in the days of MS-DOS, the disk operating system. And really, the disk is the main reason DOS existed. Multiple applications don't run simultaneously in DOS, they just have to share space on the disk. If you wanted to do fast graphics or talk to the sound card, you were really pretty much required to talk to the hardware directly. So when Microsoft came out with their mouse in 1983, they wanted it to be easy to use in DOS. And since DOS itself didn't have a framework for mouse drivers, they wrote their driver as an application that would install its own interrupt handler and then quit without unloading itself from memory. This was called a TSR, for Terminate and Stay Resident. It hooked several interrupt handlers, most importantly interrupt 33 hex, and it provided a simple API for DOS applications to interact with the mouse cursor. Even now, over 30 years later, we're still dealing with some of the consequences of this tension between the designers of the hardware and the designers of the operating system infrastructure. Drivers for tablets have to somehow fit into the system's interface for mouse drivers in order to share the cursor. When tablets first became popular, operating systems didn't have any support for their unique features, so they had to create their own application programming interfaces. Wacom has made it their responsibility to create and maintain the tablet APIs for Windows and Mac OS. Applications would have to connect directly to these specialized tablet APIs in order to get the full information available from the tablet hardware. The APIs would then connect back to the driver through some kind of side channel, so the driver could still manage sharing of the actual hardware between the cursor and the tablet API. Eventually, the operating system wants a piece of the standardization game and starts to add interfaces for things like pressure and pen tilt. But it's hard to fully replace these custom tablet APIs. They usually offer more features because Wacom can update their APIs faster than Microsoft can. This leads to a situation that's confusing for application programmers and for systems programmers. And if you're writing a driver, you have to support every available API, otherwise you risk compatibility issues with specific applications. In this case, I do have an easy way of burning through all these layers of operating systems politics between us and the hardware. With a USB analyzer device like this one, we can see the data exactly as it flows between the device and the computer. Just for comparison's sake, let's see what kind of data we get from a plain old USB mouse. When the mouse is sitting idle, the PC repeatedly asks whether there's any new data, and the mouse has to repeatedly say, nope. As soon as you click the mouse or move it, a new packet is generated. This mouse sends back packets as often as every 7 milliseconds, but only if it's detected button activity or mouse motion. Just by moving the mouse, we can get a sense of what some of the bytes are for. The left, right, and middle mouse buttons all seem to map to bits in this first byte of the packet. The next 3 bytes are jumping around a lot as I move the mouse. Those large numbers are actually small negative numbers indicating left motion, then small positive numbers for right, small negative numbers for up motion, then small positive numbers for down. And finally, this last byte seems to encode the mouse wheel motion. Usually it's FF for a downward scroll, and 1 for an upward scroll. But if I go really fast, faster than the mouse packets are sent, then you can see that it's actually a count. It'll go to FE or 2. The USB standards provide the operating system with an awful lot of structure for understanding what these packets actually mean. We can see all that in action when we plug the mouse in. So this event right here is where I plugged the mouse in. First, the hardware does a negotiation to figure out what speed the device should operate at. Then the operating system loads some of the device's descriptors in order to figure out what driver should be responsible for the rest. In this case, the descriptors indicate that this is a HID device, so the operating system will load a generic HID driver that'll then ask for some more information. In HID terminology, anytime the mouse announces that it's moved or that a button's changed, it sends back an input report. These input reports are the little 5-byte packets we saw earlier. When the HID driver is initializing, it requests this report descriptor binary blob, which is sort of like a code book for decoding the input reports. In this USB analyzer, the report descriptor is just showing up as a blob of binary instructions, but if we switch to a different tool like Apple's USB prober, we can get a parsed version of this report descriptor. The report descriptor is really just a listing of everything that's included in each report packet. That first byte is indeed a bit field with 3 bits in it, 1 for each of the mouse's buttons. What looked like 2 8-bit bytes and a mystery byte, though, was actually 2 12-bit values packed into 3 bytes. This also confirms what we expected about that last byte. It's for the mouse wheel, and it can actually take on any value from minus to positive 127. Now we have the same experiment, but with the Huion tablet connected to my laptop instead of the mouse. Now we're seeing input reports about every 3 milliseconds anytime the tablet moves around while it's in range. The biggest difference we'll see between the tablet and the mouse is that the tablet's using absolute coordinates. The mouse was just measuring how fast the table seemed to move under it, but the tablet can measure an absolute location of the pen over its surface anywhere. So we can right away see the x-axis with a minimum over here, the maximum over here, and then the y-axis with its minimum and its maximum. And then these last 2 bytes have been 0 as long as I'm hovering over the tablet surface. But when I press down, you can start to see those indicating the pen pressure, and it tops out at 7FF. And the last thing I want to point out in the raw packet is this second byte, where we can see a bit field again for the pen tip, and then for the buttons. If we let the analyzer see the enumeration process, it'll start to decode the HID reports for us. The tablet itself doesn't know anything about the monitors you have attached to your computer or whether you're in left or right-handed mode, so it always sends back pen coordinates in an abstract coordinate system, and the driver is then responsible for converting this into pixels. Here we can see the x-axis ranging from 0 to 40,000, and the y-axis ranging from 0 to 25,000. If we start to take a look at the device's descriptors, we can see a little bit of the complexity unraveling. It's quite common for HID devices to be USB composite devices, which is to say that they have multiple interfaces, each of which might have a different driver or a different device class attached. The different interfaces are really just different parts of the same device or different ways to use one device. You can think of each of these endpoints as almost like different network sockets where you might listen for data from this device. In this case, we can tell that the driver is actively listening to all 3 endpoints for data. Moving the pen around only seems to generate packets from endpoint 1, so let's look more closely at the interface associated with that. Each interface has its own HID descriptors. Depending on the first byte in the packet, it could either be a digitizer packet or a generic mouse packet. And this explains why all the packets we've been seeing so far start with 7. That's just a tag indicating that these are digitizer packets. Inside the descriptor for that packet type number 7, now we actually have a description of the digitizer packets that we've been seeing. The overall packet structure looks like what we were seeing in the analyzer too. It starts with a bit field, then it has a 16-bit X coordinate ranging up to 40,000, a 16-bit Y coordinate ranging to 25,000, and then a 16-bit pressure. So this first usage indicates that this whole section references the digitizer pen. So just like we expected, we have the tip switch, barrel switch, and it's labeled as eraser, but it's actually a secondary barrel switch. This tablet seems to be using pretty standard HID mechanisms for sending all of the information about the pen. I think we might have found our first indication of these weird hacks that always seem to turn up when there are these turf wars between standards and hardware vendors. All the buttons are producing packets that encode the button state as a regular bit field, but that bit field is stuck in what would normally be the y-axis of the pen position, and then it's using an otherwise unused bit in the button bit field to signal that this is a non-standard packet. Normally this wouldn't make any sense if you were using the operating system's built-in HID driver. But this would make a lot of sense if you were writing some kind of driver that had access to all of that raw pen motion, and you wanted that driver to also have access to these button presses. Sort of a dirty trick, but you see these in USB all the time. Most of this initialization is pretty normal, but there are these two very strange-looking getString descriptor requests. GetString descriptor is supposed to return human-readable information, like the name of the manufacturer or the name of the device. In this case, getString descriptor is being called with some suspicious and fairly large indices, and it's returning values that don't seem to be strings. This is a really strange way of putting the device into a different mode, but unfortunately you see hacks like this in USB all the time. In fact, Microsoft's own standard for shipping Windows-specific information in your USB descriptors uses a magic string descriptor similar to these. For better or for worse, Linux usually doesn't get this same treatment by hardware vendors who develop these strange features in tandem in their drivers and in their firmware. So often when you plug a device into a Linux machine like this Raspberry Pi, the drivers will go about accessing it in a somewhat different way than their Windows or macOS counterparts would. So it's handling the pen motion just fine. We're getting the same kind of input reports that we saw before on endpoint 1. It takes a little bit of configuration to get it working, but you do get pressure sensitivity with GIMP right away on the Raspberry Pi. In this case, though, the buttons are behaving totally differently. They're coming through on a different endpoint, endpoint 3, and this time they're emulating keyboard keys. Control X, Control V, Control S, Alt F4. Like, these don't really match the behaviors. Like, this button here that's supposed to be undo is actually trying to close the application. The plus and minus zoom buttons here don't actually map to plus and minus. The plus and pencil map to plus and minus. So this looks an awful lot like the firmware got all these buttons wrong, and then they have a mode for disabling the built-in keyboard emulation support and emulating it on the computer. Oh, actually this string descriptor 100 is showing up in the Linux driver too. Well, with a little bit of research in the Linux source code, I found the origin of that weird string request. It turns out that Linux does have a simple driver for this line of tablets. It includes a few workarounds for bugs in the device's HID support. This HID uclogic.c driver was responsible for sending the string request, and it claims that this odd string request enables fully functional tablet mode and returns some parameters specific to the device. Now let's take a look at the packets being sent between the Wacom tablet and its official macOS driver. Right away we can see these long, mostly zeroed packets being delivered to endpoint 2. But those aren't actually the pen motion. Well, this tablet also supports capacitive multi-touch for detecting your fingers. 1 finger, 2 fingers, 3 fingers. And we can see this is just an array of information for each detected touch point. The pen motion is coming through here on endpoint 3. And it's a much smaller packet that looks fairly similar to what we were seeing with the Huion. The first 2 bytes are a packet ID and then a bit field, a 16-bit X coordinate, and then a 16-bit Y coordinate, and a 16-bit pressure. The last 2 bytes are a little harder to figure out, but they do seem to be related to the pen's angle. That last byte goes down to 0 as the pen approaches about 45 degrees, and then peaks at around 30 hex when the pen is straight up and down. We can see that endpoint 3 belongs to interface 0, and here's report ID 2, so this should describe the packets we've been seeing from the pen. And it looks like there's a lot here, but actually this isn't telling us anything about what the data is, it's just telling us how long the packets are supposed to be. So in this case, the report ID is 2, and all that's telling us here is to expect some 8-bit values and 9 of them, and sure enough we see 9 bytes. But the descriptor here doesn't say anything about what those 9 bytes are. So unfortunately, this is also something you see pretty often with HID. HID here is just being used as a wrapper for a completely opaque vendor-specific protocol. So although we can reasonably guess what these bytes might be for by doing some experiments, the descriptors don't actually explain them to us like in a standard device. Well, that's as deep as I'm going into the protocols for now. But if you want to learn more, I definitely recommend reading the USB HID spec. And then after you've read the standards to learn how it's supposed to work, read the Linux driver source code to learn how it actually works. Alright, let's get back to the hardware. You'll start to get a hint about the differences between these tablets if you look at the pens. I have 3 tablet pens here, and they're all powered in a different way. Huion's tablet pens work on battery power. The tablet comes with a pen that uses a rechargeable battery. And you can buy spare pens that operate off of AAA batteries. Wacom's pens, on the other hand, don't need their own batteries because they're powered by the tablet's magnetic field. We should be able to use a coil attached to the oscope as a magnetic field probe to pick up the signal that the tablet is using to power up the pen. Well, that's definitely the signal we're looking for. If you look at that waveform, you can actually see the pulses moving around in time as I move the receiver coil in space. So that tells me that maybe the tablet is using this signal both to power the pen and to send the pen its own location, so that then maybe the pen reports that back along with sensor readings in some kind of packet later. It's possible that this approach makes it easier for Wacom to support multiple pens simultaneously on the same tablet. If I bring the pen into range of both the tablet and this receiver coil, things get a lot more complicated. There's so much going on that it's hard to see on the scope, but it looks like what's happening is a form of time division multiplexing, where the tablet spends some of the time sending this signal that powers the pen and gives it location info, and then the pen spends some of the time sending back a response packet, which presumably would have information from its sensors as well as information about the decoded location. If I hold the coil right next to where I think the transmitter is in the pen, you can get a much clearer view of just the signal that the pen is sending back to the tablet. Well, with this oscilloscope, I don't think I'm even going to be able to tell what kind of modulation this is using to send the data back. But if you have a software-defined radio that can handle signals under 1 MHz, then this might be an interesting thing to decode using a tool like that. So the Huion tablet, by contrast, doesn't transmit anything. As soon as you turn on the battery-powered stylus, it starts transmitting a sine wave. Likewise with the rechargeable stylus, as soon as the tip button wakes it up, it starts transmitting a continuous sine wave. So when this pen is idle, it transmits a sine wave at 255 kHz. And the amplitude is changing, but I don't think that's significant. I think what's significant is that as I press harder, the frequency actually increases to 266 kHz. And if I press the buttons on the side of the pen, I get a quick jump in frequency. This one seems to be 235 kHz. This one's 245 kHz. Well, sure enough, it's pretty easy to emulate one of those Huion pens just using a signal generator. Set it to 255 kHz, and now the pen appears to be hovering above the surface. But if I slowly increase the frequency, you can start to see that now the pen's drawing, and I can increase the frequency to increase the sensed pressure. So these Huion pens have the potential to be very simple inside. I'm curious how they're made, so let's take this one apart. The battery housing and the on-off switch are just like what you'd find in a cheap pen-style flashlight. All the electronics are in the front of the pen. When you unscrew the front of the pen to replace the pressure-sensitive nib, you can already see the transmitter coil. Well, you can disassemble it about this much without much damage. But this circuit board is heat-staked down to this plastic tube. So I'm going to try to carefully remove this barrel so that we can see the back of the board. The circuit inside the Huion pen is remarkably simple, and I think it's kind of elegant too. On this side you can see the 1 transistor, and on the other side we have the 2 buttons and a handful of capacitors. It forms a simple 1 transistor oscillator that derives its timing from the combination of a coil and a capacitance. These buttons lower the frequency of the oscillation by switching in additional capacitors. There's no sensor built into the tip, but we can certainly see the frequency increasing a little bit as we press it. Let's take a closer look at the transmitter coil. Here I have the coil removed from the rest of the pen circuit and connected to a meter that measures its inductance. The pen nib itself is made of plastic and doesn't affect the inductance of the coil. but the pressure from the nib moves a small ferrite core inside the coil that changes its inductance. This small decrease in inductance decreases the amount of energy that this stores in the magnetic field, and it slightly increases the frequency of oscillation because there's less energy that has to be converted before the oscillation can continue. Last but certainly not least, I think it's time to take a look at what's inside this tablet. We know that somehow it's going to have circuitry for detecting both the frequency and the location of that magnetic signal being transmitted by the stylus. Well, unfortunately, it looks like you have to take off all the rubber feet to get the screws out of the back. Alright, now it's coming off. 12 screws along the edges, nothing in the middle. Now we're greeted by a nice metal shield on the back. Ooh. That's deceptively simple, isn't it? So everything on here, except for what looks like just the voltage regulator, is covered in shielding foil. And then we have more shielding tape just for the edges. Each of these pieces of shielding has a specific purpose. Without this piece, the tablet would be very sensitive to electrical interference coming in from the back of the tablet. This would be especially bad if you put the tablet on top of some other piece of electronic gear like your computer. This thin piece of shielding tape along the edge seems to cover up the wiring along here that would otherwise, if exposed, provide maybe erratic sensing. Tablets use the printed circuit board itself in order to form an array of coils to receive the magnetic signal from the stylus. This tablet has a 2-layer circuit board, but it's been designed carefully, one array of vertical coils along the front side of the board, and another array of horizontal coils along the back side. These coils can each enclose plenty of area, but they only have room for a single turn of wire, so they can't convert the magnetic field into very much electricity. This receiver circuit will need to be very sensitive to the electrical signals coming out of this matrix of coils. So all the shielding helps protect this receiver from any external electrical signals. Oh, there we've got our analog front end. This square chip in the middle without any markings will be our microcontroller chip. It's got a 12 MHz crystal and it's connected directly to the USB interface. Without the labeling, it's harder to tell exactly what this chip is, but it could really be any small microcontroller with a USB interface. Each of these is a 74HC4051, an 8-input analog multiplexer. The microcontroller uses all of these multiplexers to scan through up to 32 inputs one at a time. Through these multiplexers, each input is then in turn connected to a chain of sensitive amplifiers. The designers have really helpfully added these boxes around each stage of the amplifier design. These first few stages seem to be based on these small 6-pin op-amps. This 8-pin chip that looks like it could be some kind of serial memory is actually the last stage in the analog front end. We can start to get a very rough idea of what the scanning pattern looks like by probing the enable pin on one of the multiplexer chips. It looks like the microcontroller has 2 distinct scanning modes. When the pen isn't yet being tracked, it's quickly scanning the entire surface to try to locate it. Interestingly, having the pen anywhere near the tablet, even if the position can't be tracked, will change the timing of this detection sequence. After the tracking is stable, you can actually see that it's targeting its multiplexer scan at only the location of the tablet around the pen. This probably improves responsiveness since it won't have to scan as many inputs before reporting a new location. Sometimes the scan goes away completely when I'm on an area of the tablet that isn't using this chip. So this analog front end has several outputs. This little bundle of 5 signals right there, going from the last stage in the analog front end through these vias directly under the microcontroller to its analog IOs. So in this experiment, the bottom trace is just being used to synchronize to the scanning waveform. It's just connected to an arbitrary enable input to one of the multiplexers. The most straightforward signal we have coming out of the analog front end is a very heavily amplified version of the signal from the selected coil. This isn't really useful for determining the location of the pen, but this is a great way of measuring the frequency. The signal is a bit noisy and the duty cycle isn't 50%, but the frequency tracks pretty accurately with what we would expect. This signal looks like the result of an analog integrator measuring the signal strength of the received signal at all the sampled coils. This signal seems to be the gate that turns on the integrator. It looks like when the tablet already has a lock on the pen's position, it only has to look at 4 sensors in the x-axis and 4 sensors for the y-axis. By comparing the signal strength received on each of the scanned coils, the tablet can estimate the position of the pen fairly accurately. Well, that's all I had for today. I hope you enjoyed this closer look at how graphics tablets work. These Huion tablets seem to be especially great for experimenters due to their low cost and simple operation. Please post a comment, especially if there's something you'd like to see more information about. And if you really want to help, check out the link in the description for Patreon. And thanks so much to all my existing Patreon supporters for making this video happen. I hope that I could give you some answers about how graphics tablets work. But even more so, I hope that I could give you some new questions to ask about how the things around you work. I'm especially excited to see what kinds of things all of you might build with hacked graphics tablets. Personally, I'm thinking maybe the graphics tablet would be a good position feedback device for a little drawing robot based on random motion. Well, that's all for today. Thanks for watching.